It is a great place to start, whether you have a specific application in mind or are just getting started and don't know how to begin. Thank you.
Hi everyone. In this section, we'll discuss the Grover algorithm and how to run a Grover search problem with the Classiq IDE. Search problems are incredibly common in computing. They come up everywhere. You need to find a file in your file system, a word in your document, or a variable name in your code. Computers need to do many more things internally, like finding a place in memory where they can store your data, finding the address of a specific hardware device, and so on. It's interesting that not all search problems are identical. Some are harder than others. For example, long ago, there were these things called phone books. They stored people's names and phone numbers, and they were sorted by the first letter of the person's last name. Searching through a phone book isn't hard. In fact, it's incredibly quick, as you can use the binary search algorithm to do it. You open the phone book at some random position and check if the last name where you happen to be begins with a letter that is before or after the letter you're looking for. You then open at a random position about halfway through the remainder of the stack in the right direction. Repeating this will get you to the right place in about logarithmic time. So if you have n names in the phone book, and maybe n is 10,000, then you expect to find the number you're looking for in log of 10,000, which is about 4 attempts. Not bad. Searching through the phone book is quick because it has structure. The names are sorted, and we can exploit that if we want to be quick. But not all problems are that easy. When we say we're trying to find a needle in a haystack, what we really mean is that we are dealing with something that has no structure at all. The time needed to solve this type of problem is linear in the size of the haystack. The best thing we can do is to simply check each item in the collection and see if that's the one we're looking for. How could it be any quicker? The Grover algorithm is an example of how extending the model of computation by allowing the information to be quantum allows for an algorithm that has a chance for being faster than any classical option. Instead of a runtime proportional to the number of items in the collection, the Grover runtime is proportional to the square root of that number. We call this a quadratic speedup. There are tons of resources, including in our very own Classiq documentation, where the principle of operation of the Grover algorithm is explained in depth. It's not really possible to do it justice in a quick video. Instead, we will look at how we find solutions to a simple arithmetic expression with Grover and get a feel of how it works and what the circuit we synthesize using the Classiq platform looks like. Searching for the solution for a single arithmetic expression is a simple problem. It's so simple that you may be wondering what it can teach us about quantum computation at all. The reason to do it is that it's very easy to get intuition about the results. We can look at what we get and immediately see if it's correct. In addition, there are computationally difficult problems where solving many arithmetic expressions together is required. Those type of problems can also benefit from quantum computers. So we begin with a simple arithmetic expression. Let's find all the possible solutions of the expression a plus b is equal to 1. Let's see how to run the Grover algorithm on this expression in the Classiq IDE. We first define an oracle function. The oracle is a function that flips the phase of the state for states that are compatible with our original expression, but doesn't flip the phase of states that do not. In the IDE, we define the oracle here. We set the size of each variable in the expression here. The size is the number of qubits we allocate to encode the number, just like having to allocate some bit number to encode a number on a classical computer. The oracle has the effect of tagging the correct quantum states for the next stage of the algorithm, called amplitude amplification. The effect, as the name suggests, is to amplify the amplitude of tagged states while suppressing others. This step can be repeated several times to sufficiently amplify the correct state's amplitudes. We can specify the number of times we want to repeat the amplification stage here. Selecting the correct number is not trivial, and you can find more information on how to do this in the Classiq documentation. We now synthesize the circuit by clicking on the synthesis button and see the circuit get. There are two blocks we can expand, look at the repeat block, and see it is indeed repeated the number of times we specified. Finally, let's execute the circuit on a simulator. Let's simulate on the IBM Air simulator. I'll set the execution details. We'll simulate the circuit about 2,000 times in this case, and get the resulting count histogram. We see that the A register has equal probability to be 0 and 1, and similarly, the B register has equal probability to be 0 or 1. So, indeed, we get the unspectacular result that 0 plus 1, or 1 plus 0, indeed equal 1. We've successfully synthesized and run the Grover algorithm on a quantum simulator. I hope you enjoyed this session. This is just the first step, and it already results in a non-trivial circuit, which would be hard to design manually. Things only get more complex from here, showing why automated design is so great. Thank you.
Hi, I'm Eden. I'm the manager of Classiq for Academia, and my background is in physics and electrical engineering with a master's in quantum dynamics. In this video, we're going to discuss the beautiful example of option pricing for the applicability of quantum computers in the financial field. Let's see how you can use Classiq in order to execute a quantum algorithm that tackles this problem. In financial models, we're often interested in calculating the average of a function of a given probability distribution. For example, one might want to estimate the value of an option contract on a future date. Here, we will deal with European vanilla option pricing. This means that a buyer buys the option to buy or sell an asset at a certain price called the strike price on a predetermined date in the future. The value we are interested in is the difference between the strike price and the option price. This is the payoff, which indicates how much it is worth to buy the option. Estimating the payoff to a good precision can make a real difference for financial institutions that offer these options. Therefore, we are interested in estimating the average of this payoff function, where the values of the asset itself are modeled by a log normal distribution. The most popular method to estimate the average payoff is Monte Carlo simulation. Classical Monte Carlo methods, which basically samples many instances of the strike price and calculates the average payoff, generally requires extensive computational resources to provide an accurate estimation. Quantum computers may provide new ways to solve computationally intensive financial problems. The core quantum advantage of several of these applications is the amplitude estimation algorithm. This algorithm enables estimating a desired parameter to the same accuracy, but with a quadratic speedup over classical Monte Carlo methods. Let's get started and see how to estimate these options with Classiq. From the synthesis page of the platform, we choose the option pricing example. On the right, we have the panel where we can configure our problem. First, we choose the log normal distribution for our strike price distribution. The payoff function, which represents the type of the options we are dealing with, is the European call option. The number of qubits is used to discretize the values of the asset. More qubits means better resolution, but for now we will start with 3 qubits. The threshold means the strike price. Now we first need to generate the model in order to apply all our changes, and then we synthesize our model to receive the quantum circuit. This is the circuit we have received. It uses 15 qubits and its depth is 531. Let's understand the circuit itself. We first have the state preparation, which both prepares the log normal distribution and calculates the payoff function. Now let's focus on the quantum phase estimation block, which is the main component within our amplitude estimation circuit. The top qubit here is the phase qubit, which basically stores the results of our algorithm for our final estimation. We see in the middle our control Grover operator, which acts as the unitary for which we estimate the phase. Within the Grover operator, there is a lot going on, including the use of the state preparation we examined before. I encourage you to keep exploring it by yourself with the different levels of hierarchies the Classiq visualization enables. Let's now execute the circuit and see how the results look like. Here we are in the execution page. We will use the IBM Air simulator within the Classiq platform with 2048 shots. And we see that we get, ta-da! These are the final results. As we've seen, we used 1 qubit to store the results, so we get here an histogram of only 1 qubit. By using post-processing techniques, Classiq estimates the average option price from the resulted histogram, and we can see it here. This is very nice indeed. We've been able to design our option pricing model in Classiq to generate a circuit for it, to understand it, and to extract the result from it, all with simple user interface. Let's see now what happens when we increase our problem size a bit. We now choose 3 qubits for the phase estimation to store the results, and when we generate the model and synthesize, we receive this 10 qubit circuit. We can see the same structure as before, and within the quantum phase estimation, we have now 3 qubits that store the results. When we execute a circuit, we now receive a histogram with 8 possible results. We can see the final result here on the bottom, which is not as before since we changed the parameters of the model at the beginning, but it is more accurate because we used more qubits to store the results.
In this lesson, we'll discuss another famous algorithm that's of great interest in current quantum research. The variational quantum eigensolver, or VQE, is a hybrid algorithm. It uses both quantum and classical steps to find the ground state of a system. In quantum mechanics, we describe systems by specifying a Hamiltonian. The Hamiltonian allows us to answer this question. For a given state, what is its energy? Equivalently, the Hamiltonian is that function that can be used to evolve a quantum state in time. It's all in the Schrödinger equation. In the Hamiltonian, we can encode the interactions between electrons in an atom, between those electrons and the atomic nucleus, and any other thing we want to include in our model of the phenomenon we're interested in exploring. As we know, one of the postulates of quantum mechanics is that the results of measurements of an operator are eigenvalues of that operator. Knowing the eigenvalues and eigenstates of the Hamiltonian is, in other words, what we would call knowing the states of the system. Nature is, in a way, lazy. All systems tend to gravitate towards a state with minimum energy. Let's ignore entropy for the sake of the argument. And because of that, in physics and in physics-related or inspired problems, one of the most natural questions to ask is, what is the ground state of the Hamiltonian? What's the eigenstate of the Hamiltonian that has the lowest energy? This is a simple question to ask, but in practice, it can be very difficult or even impossible to answer analytically. Complex Hamiltonians often come up in chemistry problems, where the energy state of a molecule is of interest. So it's common to see the VQE method used in quantum chemistry research. Because finding the ground state can be a difficult problem in complicated systems, we can try and do things by successive approximations to an initial guess that we think is reasonable. In the circuit model of quantum computation, a way to do this is to guess a pattern of gates in the quantum circuit that is parameterized. This means, for example, that the angles by which the quantum gates rotate qubits are not fixed. Instead, they are a parameter that we can tweak. Our guess for the circuit is called the Ansatz, which is a German word roughly translating to starting point. And the circuit we build is a parametric circuit. We can select values for the parameters and then execute the circuit. We get an output from the circuit, and we can then evaluate what the obtained energy value of that state is. But we want that to be the lowest possible value. Here comes the classical step. We update the circuit parameters, for example, by using the gradient descent method. We then run the circuit again and see what energy we get for our new state. We repeat this process several times until convergence. This, in a nutshell, is the VQE method. Now let's run a VQE algorithm in the Classiq IDE. We begin by going to the synthesis page and selecting the VQE model from our model library. The example here is to calculate the ground state of an H2 molecule. On the right-hand side, we have this already set up for us. By pressing Generate Hamiltonian, we can see it, represented as a sum of Pauli operators. We then generate the model by pressing this button here, and now we're ready to build our circuit by selecting Synthesize. The obtained circuit has blocks for setting the starting values for parameters and blocks for the ansatz itself. It's sufficiently involved for us not to dive too deeply inside. Instead, let's execute the circuit and see what we get. The plot below is a convergence plot. It shows that after a sufficient number of iterations, the parameters have converged to a value that gives us the minimum energy. Above, we can see the energy itself and the final parameter values. We've shown how to run a VQE algorithm in the Classiq IDE to find the minimum energy state of an H2 molecule. There are many more features in this module of the IDE and the Classiq platform, and you can learn a lot from reading the documentation. Hope you enjoyed this section, and see you on the next one.